So our previous discussion was about finding residuals. Actually, if you find the residual of every single value in a scatter plot, you can get a very useful tool called a residual plot. So I don't recommend doing this by hand, it would take forever, but your calculator and also computers can do this stuff for you. So on the left-hand side, I have your original scatter plot. On the right-hand side, I have the residual plot of that. And it kind of gives you an estimate of how far things are from your regression line. So what you do with this is you can look at it and see if you have an appropriate linear model. So ideally, you are going to have completely random scatter and no major pattern. And that's in the residual plot. So if you look at the residual plot on the right, the random scatter, unfortunately, it's not completely random. However, there's no major pattern, so it's pretty good. And actually, the thing that you should look out for a good residual plot is that it's boring, that there's no pattern, no shape whatsoever. So we have another term that's important to know, and that is our R squared. And actually, we usually call it R squared. The full name is coefficient of determination, but if you want to just remember it as R squared, that's fine. So remember, in the previous section that R was correlation. So if we square it, we can get the coefficient of determination. And the R squared is going to be the percent of the variation in whatever your Y is that can be accounted for by the regression line. And I'll go into more detail of this in class. If you're taking the AP test, you do need to know, and actually, unfortunately, this is one of the first things that you would have to memorize for the test. If you are not taking the AP test, I will most likely do this as a bonus, so it's optional if you know and understand this. So now we're going to do an example that includes a little bit of everything. So this has to do with the long jump and sprint time example that we did in the previous section. We are going to start by using the linear regression line that they gave us. And we're going to start by calculating a residual for a student who had a sprint time of 7.25 seconds and a long jump of 110 inches. So this 110 is his actual long jump amount, so we're going to refer to that as actual. Now remember that residual is actual minus predicted. So we're trying to find the residual. We know the actual. In order to find the predicted, we are going to use the equation that they gave us. So they give us that y hat equals 414.79 minus 45.74 times x. In this case, my x is my sprint time, which in this case is 7.25. So we're just going to plug that in. You can use your calculator on this, and you find that Christian's predicted length was 83.175. By the way, our y is in inches. So that was his predicted value. So the residual can be found, I'm just going to write it as R, by subtracting those two. Make sure that you do it in the right order, otherwise you're going to get a value that is the wrong sign. So in this case, our residual is about 20, it's about 27, it's 26.825 inches. So this means, if we interpret it, so this means that Christian's actual jump was 26.85 inches more than predicted. So our next question is going to be, is a linear model appropriate for these data? Whenever you are asked this and you have a residual plot, that's what you're going to do, is look at the residual plot. So when they're asking you about if something's appropriate, you're going to look at the residual plot if you have one. And in this case, the residual plot it's pretty boring actually. There is no major shape. It's kind of evenly scattered, so we're actually going to say yes. And the reason is because of the residual plot. So I'm going to say because there's no obvious pattern in the residuals. So a lot of people want to look at the correlation for this, which if you have absolutely nothing else, you can look at that, but the residual plot is the best way to look at it. So look at your residuals when you're asked if a linear model is appropriate. So the rest of this video is for students taking the AP test only. So if you're not in the AP class, you can feel free to watch, but this stuff might be a bonus, but it is not necessary to know. So for all of this chapter, whenever you see the letter S, and actually any other chapter, S represents standard deviation. For this chapter, however, this is going to represent the standard deviation of the residuals. And remember, the residuals are how far away your predicted value from your regression equation is from your actual value. So if you have a standard deviation of 22.38, what this means is that our values are typically going to be within 22.38 of the predicted values. So our residuals are typically going to be around 22.38. So I'll write out a nice little explanation. And so I'm going to say when using the regression model, you can just call it the regression equation also, we will typically be off by 22.38. So this is something that doesn't come up too often. You may or may not see it on an AP exam. At the very most, I would have one part of a question on a quiz about this. But if you would like to discuss this in more detail, we can talk about it in class tomorrow. So the next thing that we're going to talk about is the value of r squared. And we almost always write the r squared as a percentage, so I'm just going to change it to 70.2%. So the way that we're going to interpret this is that we would say something like 70.2% of the variation, you sometimes will hear it referred to as variability, in, and then you're going to put whatever your y value is. So your y in this case was long jump distances. So in long jump distance, is accounted for by the linear model. So now I'd like to talk about finding a regression equation from computer output. In this case, we are looking at whether or not sitting closer in a classroom is associated with higher achievement. So you have a lot of confusing looking numbers in front of you, and we will discuss all of them actually. Although there are a few things that right now you do not need to know about. So for now, the T and the P are things that you don't need. The R squared adjusted is something that you can always ignore. So the T you're not going to use in this class, R squared adjusted you're not going to use in this class. The P we will use much later on. So also right now we're also not going to discuss the standard error of the coefficient. So then everything else left here is important stuff to know. So the S, I think I mentioned in the previous slide, it's the standard deviation of the residuals. The 4.7% is our R squared, which we did talk about earlier. So now, if you look at this part right here, they say predictor, and the predictor is going to be the two parts of the equation. One of the two parts is going to be your x variable. So now, in this case, we can see that if you look at your graph, your x variable is rho. And the coefficient of that, if you remember that the coefficient of your x variable is always going to be slope. That should help you. The other thing, this one right here will sometimes say constant, sometimes it'll say intercept. So the constant is going to be your y-intercept. So all of these things should help us find our equation. And luckily they also told you that your y value is score. So this tells you to define any variables that you use. Actually, that means that's what you would do if you used y equals something plus something times x. But for this case, you can actually just write out your equation with the variables already in it. So my score is my y. Remember that your y is going to have a hat because it's predicted. So score hat is going to be equal to my y-intercept, which I said was 85.706, plus, and I'm actually going to change it to minus because my slope is negative. So it'll be minus 1.1171 times my x variable, which is rho. So that's my equation. So interpreting this slope in context, if you want, you can pause and try it on your own. Otherwise, I'm just going to work through it. So remember, slope is change in y, and y in this case is score, over change in x, which in this case is rho. And I have a slope of negative 1.1171. Remember to put it over 1. So we're going to use this to help us write out our explanation. So you can say for something like for every additional row from the front of the classroom, we predict a decrease, because it's negative, in score of 1.1171 points. So for the next problem, we are trying to find the correlation. Now remember, correlation is R. And you might remember from algebra that in order to find the R when you know R squared, so we know R squared is 4.7, which I'm going to write as 0.047. In order to find that, we are going to take the square root of both sides. Also, you need to remember that your answer could actually be positive or negative. Now, the way that you're going to know if it's positive or negative is based on your slope. And if you look at your slope, our slope is negative. So our correlation is going to be negative. And so all you need to do for this is take the square root of 0.047, make it negative, and you end up getting 0.217. So the next question asks you if a line is an appropriate model. And if you look at only the correlation and the original scatter plot, which is right here, most people would actually say no. However, what we're looking for is we want to make sure that there's nothing better than a line. Like, we can't use a parabola or anything like that. And in this case, to be honest, the line is the best that we're going to get. So, believe it or not, the answer for this is going to be yes. The reason that it's yes is because there is no pattern in the residual plot. So before we do the next example, I do want to discuss a few formulas that you're going to see on the AP sheet. And unfortunately, I think they have decided to write them in what possibly is the most confusing way possible by using B's and subscripts. But the way that the equation of a regression line is written on the AP sheet is as y hat equals b0 plus b1 times x. So you probably will be able to figure this out, but the b sub 0 is y-intercept and the b sub 1 is the slope. And we actually have two formulas that we can use to figure this out. So to figure out our b1, which is our slope, you're going to use your correlation, your r, times the standard deviation of your y values and the standard deviation of your x values. Now, to find your y-intercept, you need your slope, first of all, and you're also going to use the means of your x values in the scatter plot and your y values in the scatter plot. So let's do an example where we use these. So go ahead, read through this example, and if you feel like you can work this out using the formulas given above, go ahead and give it a try. If not, I'm going to work through it for you. So first thing that we need to do is we have to start by finding our slope. We can't find our intercept until we get that. And we're going to do that by using our formula, b1 equals the r, which is negative 0.218, times the standard deviation of y, which they give us as 10.135, over the standard deviation of x, which is 1.974. And if you calculate that out, you get your slope as negative 1.119. It's actually kind of close to what we had in the previous example, but sometimes the stuff that you have with computers is slightly different. So next thing we're going to do is find our y-intercept. And we're going to use the second formula that we have, the b0 equals the mean of the y's, which is 81.2, minus our slope, which we just found, times the mean of the x's. And if you calculate those out, we'll find that our y-intercept is going to be 85.71. So our final equation is y hat equals 85.71 minus 1.119 times x. And I do recommend that you write it out as like scores hat and row for x, but I ran out of room, so I wrote it with y's and x's.